Okay, let's move on to look at the second topic. And here in this section, I'm going to focus on the principal stresses, principal directions, and then the orientation in which the maximum strain stress will occur. So that's the two topics, but the two topics actually can be done in a single, I would say the same technique here. So here is the problem descriptions. We are given the status, and we're going to find the first one to find the principal stresses, which means we're going to calculate what is the value of sigma 1, sigma 2 in a spatial orientation sigma p, and such that the strain stress component is equal to 0. In such a spatial orientation, you can see the strain stress is 0. So that is the definition. That is the definition of the principal directions. Okay. So the definition of the principal direction is the no strain stress, and in that particular orientations, the normal stress, one will be maximum, the other one will be the minimum. One maximum, one minimum. The maximum could be here, or the maximum could be here. If one is maximum, the other one should be the minimum. Okay, so that is another definition of the principal directions, principal stresses. Okay, so that is the zero strain stress in the principal direction, and here we're using theta p. And actually later we will describe shortly, and there's a two special value of the principal directions, and not only one, actually there's a two. Okay, so that's a problem description. And then now let's take a look at how to determine those information here, and how to determine the principal direction theta p. So starting from there, we starting from the by recognizing the principal directions p is such that the normal stress are the maximum or minimum. So we simply treat the transformed normal component, stress component, as the function of theta. Then we simply take the derivative of the normal stress respect to theta equal to 0. So that is basically is the calculus, the principle of the calculus. And one rule we learned that is at the extreme value, the slope equal to 0. We simply apply that kind of equation to here. Okay, we simply conduct the derivative respect to theta and equal to 0, and at which these should be the principal stresses as our principal direction. So that is the whole equation after derivative performed like this one. So from this equation, you can quickly see by moving the terms. For example, if you move this term to the right hand side, then quickly you can determine the tangent to theta p equal to this value. So let's focus on this one. Let me transform into the graphical way. So for example, tangent to theta p, let me put a triangle here, and 2 theta p is here. And tangent theta p, maybe I can do this one here. Let me move to bottom here. So this is the value go to here, and this is the value tau go to here. So from this case, basically tangent to theta p equal to this one. Okay, so let me erase the information. You can have a better way to see it. Okay, so you can graphically using this triangle to help you to explain, to express this calculation. So this is the triangle here, the 90 degrees. So if you take the sides here, r should be the square root of the two things. So that's the r to define here. I simply define the magnitude equal to r. Okay, and then so from here you can take the arctangent. So you can obtain the theta p equal to this one. So here I box it. Here what I boxed is a formula. We're going to use it. Okay. So once we have the things, and then we determine the theta p, then that means you can, based upon this triangle here, then we can determine in this orientation theta p. That means right now we simply introduce theta equal to theta p, and to calculate corresponding the stress elements. So basically the two are the principal stresses. Okay, because here we have utilized theta p. So basically here we calculated principal stresses. So here the principal stress is what is cosine 2 theta. cosine 2 theta per this one is basically equal to r and sigma x minus sigma y divided by 2. Okay, that is cosine 2 theta p. And sine 2 theta p basically sine 2 theta p basically from this graph is r tau xy. So you simply introduce the two terms into here, in here, then you quickly do the calculation, then you should come up with the result should be equal to this one, okay? And I have done a simplification. Sigma average by definition is this one, and R equal to this one. Again, please, for the first time to learn this topic, you're supposed to introduce this one to here, and then simplify the whole equation. Then only will take you 1 minute and you will get this one, okay? In a similar way, sigma y prime, then you should have this one equation here, and that's a minimum, okay? Because one is a maximum, one should be the minimum. And again, I box is the equation, you're going to use it. And then again, we plug in 2 sine 2 theta cosine 2 theta p to here, then that should be equal to 0. If not equal to 0, that meaning you have some calculation error. So basically here provide you a checkpoint, okay? So that is for the principal stresses, principal directions. In the similar way, the different topic, we want to determine the maximum shear stress. And again, here we use this relation. We simply take the derivative, okay, derivative of this relation with respect to 0. So that means we're going to find the extremal, the values of this function. So we take this the calculus rule here. So proceed this one again, following the same process. Then you should be able to find, say, from this equation here, you can find the tangent 2 theta. Okay, and here the theta s is to indicating that is the orientation. The theta s is the orientation that the maximum shear stress occurs. So that's called the theta s here. And as a different from the theta p, basically that is the kind of the common nomenclatures we use. Okay. So here the 2 theta s is like this one again. Let me do this one here. Maybe you can like to do is this. You can simply rewrite it. That is tau xy, and then you put a minus and 2. Sorry, let me redo this again. So this one, okay. So this equations basically is equal to minus tau xy and then sigma x minus sigma y divided by 2. Okay. So with the two phase information, I build up another triangle here. And again, one side is negative. The other side is this one. Okay, basically tangent 2 theta s is something like this one here. Okay, so that's an angle here. Again, this is the 90 degrees. So this side has the same value r, okay, and then from this case, and so that's the 2 theta s, and so let me erase the unnecessary informations. Okay, good. So now this is our calculated result. And this one is what we obtained from the previous slides. If you go to the previous slides, and that is this one here. Okay, that's the equation I simply copy to here. So combining the two things together, we can quickly see that the relation is something like this one here. Okay, if we have a such relation that simply tell us is this. Again, I copy from the trigonometry equations. If tangent alpha equal to something like this one here, then basically saying the two angles together have these relations. The two angles in together have such a relation. Okay, plus minus 90 degrees. So using the simple trigonometry equation, then we can quickly find it is this one. So how can we tell this equation? How can we apply this equation? This equation is saying that as long as you find the theta p, then you simply plus minus 45 degrees, you can get a theta s, and vice versa. So that means you don't need to repeat all the calculations. As long as you have calculated theta p, then plus minus 45 degrees, you can get theta s. Okay. So now we determine the values of the components in theta s here. So basically here theta p plus 45 degrees or theta p minus 45 degrees, and that is the orientation of where the maximum strain stress occurs. And the value of the maximum strain stress, simply plug in theta equal to theta s, and again here using this triangle here, for example sine to theta s will be equal to r sigma x minus sigma y divided by 2, and cosine to theta s will be equal to r, and here using minus because here we have utilized the minus sign here. So with the two values, you simply plug in here and here each of these terms here, then you can quickly come up with this information here. The maximum strain stress actually equal to r equal to this value here. Okay, the maximum strain stress equal to r, the sites. Okay, so those are the box information. We can quickly look at the example here. So for example, we are given this case, and we're going to determine first one, the principal strain and the principal stresses, then the maximum stress, and then the orientation. So which means we want to determine sigma 1, which means sigma 2, or say sometimes people like to say sigma max and sigma min. Okay, and then theta p, so that is the A and B. Then the C basically want to find the maximum strain stress and the theta s. Okay, so we know that the theta s basically equal to theta p plus minus 45 degrees. So basically that is kind of the calculation. So the remaining we simply just plug in all the formulas, and we know, and here is a very quick substitutions of the equation we box, and you simply plug in. And again, here to remind you, when you still apply the sign conventions. For example, this is, say, if you define your coordinate system xy like this, then sigma x equal to 50, that is tensile, positive. Sigma y, and here is 10 compressive, so minus 10, sign convention. Tau xy, again, per our sign convention, that is 40, positive. Okay. So now you do the calculations, say you plug in these equations, and then you find this theta p equal to this angle. So 26.6, that is a positive angle, so counterclockwise. Per our sign convention, your calculated result is positive value, indicating when you draw it, you must be counterclockwise. Again, that's a sign convention. Okay, so 116 degrees, and again this is a counterclockwise. So let me do this one here. So this is a given one, xy. So counterclockwise by 116 degrees, so that will be something more than like this. Okay, so from here to here, that is 116.6 degrees. Oh, sorry. Okay, so that is our x prime, and normal y prime. Okay, so that is the element, the stress element, so that is the sigma x prime, and being calculated, so that should be equal to one direction is 70, one is the 30. Okay, so that is the for the principal stresses. And then for the maximum stress, and again we simply plug in this formula here, and that is plus 45 and minus 45 degrees. The maximum strain stress equal to R, if you remember that formula, R. Okay, so again, let me plug in here. So remind us, the maximum stress, strain stress have a value equal to R here, and R equal to this one. Sorry, and here is just so many formulas, and you need to prepare a cheat sheet with you when you do the calculation, the exercise for the first time. Okay, but that just simply apply the formula, very straightforward. And now once we apply this one, then you can see, for example, this is a negative one. So when you graphically represent this case, that's the 18.4 degrees negative. Per our sign convention, negative, that means clockwise. So when you draw it in clockwise wise, and then here, this is the x prime direction, this is the y prime direction, and that transforms from our originally defined xy. Okay, so that's a kind of graphical representation. Do it this kind of uniquely and correctly. Okay. So, and again, the normal stress, and again, the normal stress equal to the average. Okay, so that we simply plug in the equation here. And this is the sample example here, and this problem probably we have seen in the combined loading. So here I simply want to kind of do the kind of streamline and to integrate what we have learned from the first portion, which is we determine the stress components from each loading type, and then we from there move on. We want to transform the stress here. Okay. So for this case, we simply want to determine the principal directions and principal stress at point H here. So at the very first step, we need to determine the components of the stress here. Okay, so here we simply apply the combined loading. In terms of the coordinate systems, here we define the x, y, z like this one here. Okay, so that means we pick a stress element, something like this one showing here. Okay, something like this one. So let me highlight this stress element. So that is the stress element we're going to demonstrate. So here is the stress element, and from this orientation, this is x and this is y. Okay, x, y are the same as we defined this one here. So we simply want to determine the sigma x and sigma y and tau x, y first. Okay, let me ignore the other two sides. Basically, that is symmetric. And so how to determine the three components? Again, go to the chapter 8. We've been discussed about the combined loading. And there we have quite a bit exercise, and go for there for details, basically for this case. And you can see we have 3 loading types. So basically here we have said, kind of remind you the load type. And so here is a P for the normal stress, P divided by A for swing stress equal to 0, and then we have torque. So tau equal to Tc over J. Okay, this is 0, and we have a moment. So moment, the magnitude is my over I, and then for this case we determined, and so say this is the moment, this is the neutral axis about which the moment applied. So the point H is here, so this should be in tensions, this is in compression, so there's a tension here. And y is a distance from here to here. Okay, I is a moment of inertia with respect to the neutral axis. Neutral axis, for this case, if you look at this carefully, the neutral axis is the x. Okay, so I is about the ix. So quickly, so that is the things here. So kind of remind you, and so let me erase the information. Good. So once we determine, then basically we have the stress components. So that is the starting point of the transformation of the stress. I would say that is the starting point, and actually is the end of our learning about the combined loading. To this step, probably you should have spent maybe about 20 minutes, 15-20 minutes, depends on the fluency of your skills here. Okay, but that's a starting point. So we have those kind of the elements, sigma equal to 0 and y equal to positive 8.84 and tau equal to positive 796. So that is the starting point, and now we begin to, from here, we given those information to find the maximum principal stresses, principal orientation. Then the remaining we simply plug in our formulas described in this section.